So the natural progression, at least in my mind, when I'm thinking about, the cyclic nature of monosaccharides and their hemiacetal structure is, how do these molecules progress to complete acetals? Remember that one OH and one OR group is a hemiacetal, so if we have a carbon chain and we have one OH group and one OR group, that's a hemiacetal. So hemiacetal. And if we have two OR groups on that carbon chain, it's a full-blown acetal. So two OR groups or two alkoxy groups is an acetal. And this carbohydrate right here is a hemiacetal. You can see this is kind of the carbon that would be in the center, and we've got one OH group and one OR group over here. And we want to know how it progresses to an acetal. And well, it actually progresses just like it would if this wasn't a cyclic carbohydrate. So the anomeric carbon, remember, that's the carbon right here. That's the carbon that was formerly the carbonyl carbon before the ring closed. Now it's the anomeric carbon, and it's attacked by another nucleophilic alcohol. So another nucleophilic alcohol comes in, and the carbon is oxidized and loses this hydroxyl group right here in the form of water in order to make room for the OR group or the alkoxy group. So we have loss of water, and we've made room now for the alkoxy group, and the product then is an acetal and kind of looks like this. So now the carbon has two OR groups. And when this happens in the context of a carbohydrate, we call it a glycoside. So that's kind of a special kind of name, a glycoside. And what happens is we're able to add a functional group onto the carbohydrate. This would be the functional group, and we say that it's bonded by a glycosidic linkage. So that linkage right there would be the glycosidic linkage. Really, that's the big picture idea, but what I want to do in this video is I want to show you the actual mechanism. Of course, this is an organic chemistry type idea, so we have to go into the mechanisms, but I want to show you how this actually plays out. So let me kind of clear some room here, and I'll tell you, I went ahead and I pre-drew kind of the backbone for this mechanism just to kind of save you the endurance of having me draw out all these little diagrams. But I'll try to walk us through and I'll show us kind of the functional steps for what's going on here. So right here we have beta D-glucose. So we've got the beta anomer of D-glucose. And so this is a hemiacetal. We've got the OR group and the OH group. And what happens in the presence of kind of a mild acid is this OH group right here on the anomeric carbon gets protonated. So gets protonated, and the chloride atom is good at accepting those extra electrons from its bond. And what happens is so the OH group lost electrons to the proton, and now we have a cation right here, and what happens is we have water loss, so H2O loss. So this group right here will leave. We've got H2O loss, and then we have from the previous step this additional chloride anion. So we've got that chloride anion, and you can see that when we lose that water, we end up with a carbocation right here, because these electrons left. We've got this cation right here, and it happens to be, as you can see in this image, resonance stabilized, and that's important. This product right here is resonance stabilized. So it's resonance stabilized, and we have the planar nature of that is going to be important in steps 3 and 4. So let me kind of pull those in. And we've got steps 3 and 4 here. So we start with this planar carbocation. And it's the planar nature of this carbocation that's going to allow the next alkoxy group, the nucleophilic alcohol, to attack from above or below. So we've got the above attack kind of on this top shelf, and then we've got the below attack on the bottom shelf of the mechanism. And so the alcohol group has nucleophilically attacked, and now the oxygen atom right here has a positive charge on it, but those chloride anions that we lost in the previous step come back into play here and accept that extra hydrogen back, allowing the electrons from that bond to go to the oxygen. Same thing down here. And that oxygen loses its positive charge, and we end up with our products. Now, the planar carbocation nature of that intermediate product allowed the alcohol group to attack from above or below, and what that means is that our glycoside, just like our carbohydrate, formed two different anomers, the beta anomer and the alpha anomer. Our glycoside does the same thing. So if the additional OR group right here is cis with respect to that last carbon, we end up with the beta glycoside. And again, if it's trans, we end up with the alpha glycoside. And these glycosides, they actually occur naturally, and a few of them are quite significant. The one that really stands out to me is digoxin. It's a medication that's given for different cardiac or heart complications. Let me draw a little heart here. And it's actually still extracted from the foxglove plant in the Netherlands for use as a medication. It stands out to me because as a nurse, I've given this medication several times. But anyway, it may have occurred to you at some point over the last few minutes as we've kind of gone through this mechanism that if an alcohol can join onto a monosaccharide, and remember that's essentially what we're doing in the formation of this glycoside, that the additional alcohol could be another monosaccharide. Remember that monosaccharides have plenty of hydroxyl groups, and that this reaction could be a means of joining carbohydrates together. And if that's the observation that you made, that's a really a super astute observation. This is indeed the method by which carbohydrates join together, and we call these linkages glycosidic linkages. And of course, we'll talk at length in the future about the polysaccharides that are produced. I'm going to do a whole video on polysaccharides, but this is the means, this glycosidic formation, by which these chains are produced. But before we jump away from the actual glycosidic linkage subject, I want to point out that this whole process of forming glycosides can happen in reverse. So these linkages can actually be broken down as well. And remember that with this bond formation, we lost a water molecule. So this was a dehydration reaction. So in reverse, what's going to happen is we're going to add water back in a process called hydration. And so because we see a hydration reaction that breaks down these polyunit molecules, we call it a hydrolysis reaction. This is glycoside hydrolysis. The lysis for the breaking down, and then the hydra as a reference to the water molecule coming in. So what happens at the beginning is that the alkoxy group that we added before, that OR group, is protonated. And after protonation of that acetal OR group happens, we lose it in the form of an alcohol. So we lose that acetal alkoxy group. We've kind of formed some water right here as we lost this extra proton on that hydronium anion. And again, what happens, just like in that previous step, we form a resonance stabilized carbocation again. It's like we're forming that middle product again. So this right here is resonance stabilized. So again, the beginning of steps 3 through 4 with glycoside hydrolysis is going to be a planar carbocation. So again, we've got a planar carbocation right here. And again, what that means is that the water that comes in now is going to be able to nucleophilically attack above or below this molecule. So again, we've got the above and the below and the below. And we'll see what happens. We've got an H2O that comes in right here. And the extra electrons on that water molecule's oxygen are going to come in and they're going to nab that proton, and these extra electrons from this bond are going to come back in and they're going to stabilize that hydroxyl group. And the same thing would happen in the below situation. We've got H2O, the extra electrons here, nab the hydrogen, nab that proton, the electrons from the bond shift down and stabilize that hydroxyl group. And what we've done, because of that above or below attack, is again we've formed the beta anomer of D-glucose right here, because this hydroxyl group is cis with respect to that last carbon. So beta D-glucose, and we've formed the alpha anomer. So alpha D-glucose. And if the terms beta and alpha and anomer are confusing, I covered those in a previous video on the cyclic formation of monosaccharides. But that's kind of where you'll find that terminology. And I guess again right here we've reformed that hydronium, because now the water molecule has picked up that extra proton.